For centuries, sailors whispered stories of giant ocean monsters, walls of water that appeared out of nowhere, smashed wooden ships, and vanished without a trace. But for a long time, scientists dismissed these tales as simple maritime folklore. These mythical giants are known as rogue waves. Today we know they are not myths. They are real sudden and highly destructive ocean waves that occur in the deep open ocean, far away from any shallow coastal waters. To understand how scientists define a rogue wave, we first need to look at how we measure the ocean. Oceanographers use a metric called significant wave height, which is the average height of the highest one-third of waves. Specifically, a wave is classified as a rogue wave if its height from trough to crest is more than double the significant wave height of the surrounding sea. If the typical high waves are 10 meters, a rogue wave is 20. Many people confuse rogue waves with tsunamis, but they are completely different. Tsunamis are caused by underwater earthquakes. They have massive wavelengths and are almost invisible in deep water, only rising as they crash into shallow coastlines. Rogue waves, however, form directly in the deep ocean and have relatively short wavelengths. They appear as a nearly vertical, terrifying wall of water, preceded by a deep, hollow trough that sailors often describe as a hole in the sea. So, how did these monsters form? The simplest explanation comes from linear wave dynamics. In linear physics, ocean waves behave like independent entities that can pass directly through one another without changing each other's fundamental physical properties. This relies on the superposition principle. Imagine a giant trampoline with 10 people jumping at random. Their small bounces represent normal waves. If by pure coincidence, everyone bounces at the exact same millisecond, their forces combine. This synchronized bounce launches one person incredibly high into the air. In the ocean, this is called constructive interference. When multiple wave crests meet at the exact same point, their heights temporarily add up to create a single giant wave. This can happen through spatial focusing. Because wave speed in deep water depends on wavelength, longer waves travel faster than shorter waves. As a wave group moves, faster moving waves can catch up to slower ones, piling up into a peak. It also occurs through temporal focusing, where waves align perfectly in both space and time. Additionally, crossing seas where waves generated by different storm systems intersect from different directions can create brief towering wave peaks at their intersection points. But there is a major problem with this linear theory. Statistical models based purely on linear physics predict that a massive rogue wave should only occur once every 10,000 years, yet modern observations prove they happen far more frequently. This means linear physics is not enough. In extreme sea states, waves stop behaving like independent entities. They begin to interact non-linearly, stealing energy from each other. To model this, scientists turn to quantum mechanics. Specifically, they used the Nonlinear Schrödinger Equation, or NLSE, originally developed to describe light pulses in fiber optic cables. This equation balances two competing forces in deep water wave dispersion and nonlinear energy focusing. Under the NLSE, we observe a phenomenon called modulational instability. When waves exceed a certain steepness, the sea state becomes unstable. Instead of sharing energy fairly, waves begin to transfer energy rapidly to a single central wave. Think of this nonlinear sea like an energy bully at a buffet. While normal waves share energy, this bully wave walks down the line, stealing energy from the waves directly in front and behind it, leaving its neighbors starved and flat. In mathematics, these nonlinear wave solutions are called breathers. The peregrine breather is the ultimate mathematical prototype of a rogue wave. It starts from a flat background, focuses into a massive peak 3 times its original height, and then completely vanishes. To measure this instability, oceanographers use the Benjamin-Feir index. This index compares wave steepness to the spread of wave frequencies. A high index indicates a highly unstable sea state where nonlinear energy focusing is highly likely to occur. For a long time, all of this was just theoretical. But on January 1, 1995, science finally caught the monster. A gas platform in the North Sea, called the Draupner platform, was struck by a massive wave during a major storm. The platform was equipped with a downward-pointing laser rapid-visor. While the surrounding significant wave height was 12 meters, the laser recorded a single towering wave crest that reached 25.6 meters from trough to crest. This Draupner wave was the first hard scientific proof that rogue waves existed. It forced physicists to rewrite their wave models. But while scientists were celebrating this digital proof, shipbuilders were realizing the terrifying danger these waves posed. In 1978, the MS München, a state-of-the-art German cargo ship, vanished in the North Atlantic. The only wreckage found was a lifeboat, normally stowed 20 meters above the water, ripped from its steel pins by an extreme upward force. In 2001, the cruise ship MS Bremen was struck by a 30-meter wave in the South Atlantic. The wave smashed the bridge windows, flooded the electronics, and caused a total power blackout, leaving the ship drifting helplessly for hours. Then, in 2005, the Norwegian Dawn cruise ship was struck by a 21-meter wave off the coast of Georgia. The wave smashed windows on the 9th and 10th decks, flooded cabins, and injured several passengers. Why are rogue waves so destructive? It comes down to hydrodynamic pressure. Standard cargo and passenger ships are designed to withstand wave impact pressures of approximately 15 to 30 metric tons per square meter. But a rogue wave acts like a steel sledgehammer, striking with pressures exceeding 100 metric tons per square meter. This extreme force easily crushes hatch covers, bends structural steel, and shatters reinforced bridge windows. To make matters worse, rogue waves often appear as a series of three giant waves known as the Three Sisters. The first wave damages the structure, the second floods the decks, and the third capsizes the vessel before it can recover. The economic cost of these encounters is staggering. A single large container ship loss can exceed $150, 000 to $300, 000. Globally, the maritime industry loses 50 to 100 large ships annually due to severe weather. For cruise ships, repairing structural bow and bridge damage can cost between $0 and $0 in dry dock. Installing reinforced thick laminated steel frame store windows on the bridge costs under $50, 0 to $500, 0 per vessel. To protect these vessels, modern ship design has evolved. Engineers reinforce bow structures and place critical electrical generators higher up. Today, we also use space technology, synthetic aperture radar from satellites to scan the ocean for steep waves. Subscribing to routing software using satellite data costs shipping lines $5, 0 to $15, 0 per ship each year. Meanwhile, launching a specialized radar oceanography satellite costs between $200, 0 and $400, 0. Once dismissed as sailors' myths, rogue waves are now recognized as real predictable products of nonlinear physics. By studying their equations, we can build safer ships and guide them through the world's most dangerous oceans. Understanding the ocean's greatest mysteries keeps us safe as we explore our world. Thank you for watching this episode of Layman's Field. We hope to keep bringing knowledge for everyone.